Hi everyone, my name is Lauren Hawker-Zafer and this is Redefining AI. Redefining AI is a podcast hosted by Squirrel and the Squirrel Academy. The podcast focuses on key narratives and discussions that drive digital innovation and help people understand artificial intelligence, machine learning, insight engines, and the insight era. Now today, I've been joined by Dr. Oktay Arslan. And I am, as always, enthusiastically excited about the discussion that's coming up. Oktay is currently an AI robotics research engineer at the Acubed, the Silicon Valley Innovation Center of Airbus, where he works on various autonomy projects in the Wayfinder team, such as autonomous landing for commercial aircrafts, sensor fusion, and certification of autonomy software. Now, Oktay's academic research focused on planning, machine learning, computer vision for robotic systems, and autonomous vehicles. Previously, he was a Staff Autopilot Software Engineer at Tesla Inc. And in this role, he contributed to the development of autopilot software, namely behavior planning, path planning, and controls for Tesla's Model 3, S, X cars. He implemented the traffic-aware lane change and merging behaviors in navigate-on-autopilot feature and path planner for smart summon feature. Now, prior to his role at Tesla Inc., Oktay worked as a robotics technologist at NASA, Caltech Jet Propulsion Laboratory, where he contributed to several autonomy projects for various robotic platforms, such as quad rotors, Mars rovers, and spacecrafts. Now, Oktay, he obtained his PhD degree in robotics, a dual MS degree or dual MS degrees in computer science and aerospace engineering, all from the Georgia Institute of Technology. He also earned an MS degree in defense technologies and dual BCS degrees in computer engineering and electrical engineering, all from the Istanbul Technical University. Before we invite Oktay into the conversation, I want to start by setting the scene a little. Automation is the application of machines to tasks once performed by human beings, or increasingly to tasks that would otherwise be impossible. Although the term mechanization is often used to refer to the simple replacement of human labor by machines, automation generally implies the integration of machines into a self-governing system. Automation has revolutionized those areas in which it has been introduced, and there is scarcely an aspect today of modern life that has been unaffected by it. Welcome, Oktay.
Thank you, Lauren. Thank you for having me for today's podcast.
Yeah, it's a real honor to have you here and to have you on the show. And I'm looking forward to what I hope will be a really interesting discussion.
Yeah, likewise.
Where are you just now?
I'm right now in California. My company has an office in Sunnyvale. I work in the office, in Sunnyvale office of the company.
Mm-hmm. And do you enjoy it? What sort of weather are you having at the moment? In Europe here, we're obviously based in Zurich, and it's a beautiful summer's day.
I think it's great. We don't have winters here, I would say. It's always sunny here.
Okay. And you come originally from Istanbul, that's correct? Or
Yes, I'm originally from Istanbul, Turkey. And then after graduating from my school, I moved to US for my graduate level studies. Then after I finished my school here, I decided to stay here to work on autonomy and robotics projects.
Excellent. Now, I mean, as I introduced you at the start, let's say like NASA, Tesla, Airbus, robotics, computer science, defense technologies, computer engineering, electrical engineering. Now, my first comment I would say would be, wow. I mean, your resume is powerfully impressive. And my first question then would be how? What drove you to this type of achievement? I mean, some people speak about patience, persistence, hard work, luck, and many, I think, successful professionals, they would define the foundational key to success differently. And also, I think, from divergent angles. So, Oktay, what's your angle?
Well, I always want to learn how to implement things in real world. That's why I wanted to study robotics. So I first started my undergrad degree in electrical engineering. It was a good program, and I was learning how to understand the electrical motor works, how to control them. But then I realized all of these things are going to be controlled by softwares, computer software. Then I said maybe I should learn more about like programming, how to write good software. That's why I decided to follow like a double major program in computer engineering. So I learned programming there. So then in 2005, I think there was a competition by DARPA. They tried to develop an autonomous vehicle that can drive by itself. The first two competitions were about driving in a desert-like place. And the last one, the third one, it was called Urban Challenge, and they were trying to drive in an urban city. So I love that project, and I said, I'm gonna be working on these projects in the future. But whenever I was trying to work on autonomous driving or robotics, I realized there were missing things that I didn't know.
Mm-hmm.
For example, I don't know the mechanical systems. I don't know how to program on these platforms. That's why I said, okay, maybe I should study this subject as well, and I should study this subject as well. And I think my my accomplishments are based on how much I don't know about a subject, and I want to learn those subjects. Not like not like a very simple way. Like if you want to do something, if you want to develop something in the real world, you have to know almost all details. That's why you have to study to the finest details. And I thought I could achieve that by taking classes and go to school. University is a very nice environment. It gives you like so much opportunity to learn things if you want to work hard, I would say. And I think I went to two great schools. They were technical schools, and they had lots of opportunities to provide for anyone who wants to research in this field. And I just took my time and enjoyed that environment and tried to learn as much as I can before I leave academia, I would say.
Mm-hmm. I mean, that's inspiring in itself. And I would maybe say that what I identify that is more of a really close-knit passion to want to actually do what you do well. I mean, I think it takes a lot for someone to identify components of their industry that they don't know and then try and pursue that and learn more. I mean, would you classify yourself as a lifelong learner?
I think like I can say that, but before we have to make a definition. Like when you say I learned something or I know something, what do you mean by that? So for some people, you buy a book and you read a couple of pages, then you can put that in your resume. You can say, hey, I learned this subject. But we know that that's not the case in most of the time. I think in my definition, in order to say that I know a subject or I learned this subject very well, I think you have to take fundamental classes in that area and you have to know them well. Then you have to work on a problem and you have to implement something and you have to make sure it works in your lab. Then you have to deploy that thing in the real world. And then maybe you can publish something about what you achieve or what you kind of learn in academic community.
Mm.
And then maybe you should be able to teach that subject to someone who doesn't know. And I think if you have all of these things, then you can say, I know a subject, I would say. That's my definition of knowing subject.
Mm-hmm.
Other than that, if one of the items is missing, I cannot say I know this subject. That's why I don't want to put something on my resume. I think that's my definition of knowing something. And throughout my life, I tried to do these things in different settings. Sometimes I was in school, sometimes I was in industry. But I think learning the fundamentals and learning by hands-on experience and being able to explain these things to someone who doesn't know, I think that's my definition of saying I know a subject very well.
Mm-hmm. Mm-hmm. That's quite a lot of success metrics and criteria, which is admirable.
I mean, that's the definition of being an expert in a field, I think.
Of course. And today, I mean, so now you've progressed so far that you're now embodying the role as the AI robotics research engineer at the Acubed. And this is obviously the Silicon Valley Innovation Center of Airbus. So maybe you can start to tell us a little bit about what are you working on in this role, and what then would be my question, what lies within the scope or under the definition of innovation when it comes to Airbus?
Sure. We are in Silicon Valley, and this place is known for good software engineers, good hardware engineers, and nowadays I think it's a hub for AI talent. I think Airbus opened this office here just to attract more AI researchers to work on autonomy projects for the future Airbus products. There are some autonomy projects like autonomous landing or autonomous taxi, autonomous takeoff. And we would like to leverage the state-of-the-art AI techniques to solve these problems whenever necessary. My job is like I work on mainly like something called like perception. It's like when you try to develop these vehicles, they have to operate in an environment and they have to understand what their surroundings look like.
Mm-hmm.
And in order to solve that problem, we use various sensors. Like this can be a camera, this can be a GPS sensor, radar, or whatever. So usually we have lots of information from this sensor, and you have to kind of filter out and put them together to compute a meaningful information about surroundings, so that this vehicle can make a decision by itself.
Mm-hmm.
So that's kind of my role here. I work as a member of the perception team, and we usually use camera sensors to understand what's around the vehicle. And there are also other projects like I think the company is investing to autonomous flight technologies a lot. They want to make things autonomous, or at least more automated for the future aircrafts. And that requires so many researchers like me, like who have background in AI robotics to contribute this field. That's kind of a common trend in the Bay Area. I see more companies are trying to put automation or like autonomy in their products to achieve safety, productivity, more productivity, or like a profit in other businesses. Mm-hmm. But I think the trend is like I've started to see this trend like in like taxi business or agriculture, truck automation, self-flying taxis. Like there are so many different businesses that previously done by human, and now companies are investing to automate them.
Okay. I mean, like a driving question, and I can hear a lot of people outside of the podcast maybe asking this, but what is spurring on innovative approaches to automation or more of an automated approach? Like, what's the necessity? What's the necessity for it to develop more? Mm-hmm. And is it replacing something? Is it solely for a component of innovative product development and design? Like, what's pushing it? What's driving it?
Yeah, I think I can give my share for this answer. It may not be true, but that's my opinion. And because like this AI or like robotics, we are trying to do something that hasn't done before. So it's okay to have different opinions on the subject. And I think like at some point we had robots, and they were developed in the university laboratories. Then it went from there to factory assembly lines, like especially for automotive industry. Now we see those robots are coming and becoming part of our daily life. We have Roomba, like the floor cleaner machine.
Mm-hmm. Mm-hmm.
And then now we have self-driving cars driving on the streets, and probably we will see more vehicles in the sky. I mean, we already have some drones flying around, but maybe we have like passenger aircrafts or cargo aircrafts for some like transportation requirement, I would say. So I asked this question to myself. So what happens so that we start to see these vehicles on streets, and what happened that we start to see these vehicles doing operations very closely to human, especially when you drive on streets. Like you have to be careful, but there are pedestrians, and you have to understand what they are doing. So I think the biggest improvement there was about. We have lots of machine learning developed approach, and by using this data-driven approach, we can understand the surrounding of the vehicle. Previously, we didn't have this capability. Like we did not have these machine learning algorithms that can understand, oh, there's a traffic light in the scene, or there's a pedestrian, or there's a vehicle. We didn't have this capability. We had some, I would say, classical vision, and it was helping us to solve some of these problems. But so whenever we couldn't achieve a human level accuracy, we would try to simplify the problem. And when I say that, like, let's say you want to deploy a vehicle, but you don't understand the surrounding, maybe then you can control the surrounding so that nothing can intervene in the operating environment, like factories. I know when I was a student, I went to a car assembly factory, and I know there was a big, huge robots. They were doing like welding, assembly, all these various tasks. But whenever a human was attending that like assembly area, the entire robot process would stop.
Okay.
And then you had to wait until the person leaves the area so that the robot can return to automation, sort of automated tasks. So it's like whenever we cannot solve this perception problem, we tend to kind of restrict how to operate these things. If there is a moving thing, I don't know what it is. That's why it should be safe and it should stop. But then we cannot do that for self-driving cars. So when a car drives, you cannot say, I see something and I don't understand what it is, I should stop. So what happened is like we try to use lots of data, and we collect lots of data, and we try to label them and say, hey, this is a pedestrian, it's a traffic light, or this is lane information. So we kind of use this labeled information, and we try to use these new machine learning models to train, so that we can understand whenever we see an image, so we can understand what is in the scene. I think that was the key to achieve these this level of autonomy in robotics.
Okay.
Before making your own decision, I mean, you have to understand what your surrounding looks like and what are the moving things.
Of course, and
yeah.
I mean,
you have to understand their intention, so that you can be a little bit smart about what to do for yourself. Otherwise, I mean, we cannot walk in a dark night. We have to wait, and we have to use some light to shed light around so that we can understand what's around. That's very similar to for robotic software. I mean, you have to understand your surrounding first before making anything smart.
And how are you? I mean, you've mentioned a couple of times there that you're trying to implement the latest AI techniques. You've mentioned machine learning algorithms that are used to build models, etc. Are you using, and I'm just taking maybe from interpretation and trying to make my own interpretation as to what you're conveying there, is it a lot of image classification, especially in terms of perception, or are you using like deep learning models? What sort of techniques, AI techniques and machine learning algorithms, what direction do they go in terms of capabilities?
I can talk about I can talk about like self-driving cars because that's more.
Yeah, sure. Yeah.
It's a richer domain because when you fly in the sky, there are not that many objects. So it's very. We have problems there, like we have technical problems, but I think driving a vehicle, I would say, in a busy San Francisco street is a challenging task.
Okay, why?
Yeah. So I think like when you try to drive something on a highway, you have to have some information to do planning and control. The first thing is like you have to understand what are your lane markings and how many lanes do you have, and for each lane, how many vehicles are there, and what are their relative position with respect to yourself, or what are their velocities. So you have to have this minimal information. And I think among all of this information, the most critical thing is like, is there a vehicle in front of you? So you have to maintain a safe distance. So you can use some classical, I would say, widely used sensors like radar or ultrasonics. But I think the main trend is to use cameras. So when you use cameras, then you have an image, and when you show the image to a human, it can identify those objects very quickly, because it's very easy to understand what a car look like for a human. But for computer software, that's a little bit challenging because they don't see the way we see things. They just see a bunch of numbers, like zeros and ones, maybe or 0 to 55, like, or they see like some values for it's like red color, red, green, blue channels. So you see from computer perspective, you see a bunch of numbers. Then from this number, you have to kind of look for a pattern that resembles the object you are trying to find. And that's very time consuming. Like you have to have enough compute power. Plus, you have to we use something called like supervised learning. So what we do, you show a bunch of images and you label them by human. Then you train a model. You classify. Then you train a model. Then when you deploy that model on the car and you show an image that is not seen before, and it kind of try to classify those objects. So this is the general trend, because we have more data nowadays, and also we have more compute compared to 10 years ago, maybe 15 years ago. Like these ideas in machine learning are not. I mean, there are some key developments, but they've been used like since the 1990s. I know, like the early papers. But at that time, we did not have fast computers like hardware, and we did not have enough data. And in the last 10 years, we start to have faster. I'm not going to say CPUs because we have GPUs, like graphical processing units. So we start to have these new hardware, and they have so much compute power. And then we start to have cell phones or lots of cameras. So we start to have lots of data. So we have, and these are the like two prerequisites for developing a good ML model. You have to have compute and you have to have data. But then we had some algorithmic challenges, but then we start to have some key ideas in the AI community. And these key ideas came from based on like lots of insight and lots of experience by like very senior researchers. And when you have these three key developments, like faster computers, more data, and smarter algorithms, then we start to train these ML models, and they achieve accuracy better than human for some classification tasks. We have like some classical like challenges like ImageNet, like in an AI community. So whenever you say I have a new model, well, there's a standard database, you test your model on that and try to benchmark how good your model is. And I think there were like this AlexNet paper sometime in 2012 they achieve an accuracy that is very, very high than the second one, I think. And that was the key moment. People, they say maybe we should use these deep learning models to solve these machine learning tasks. And every year there were more deep learning based approaches in the community, and they did much better than any other counterparts. But then gradually we start to have these machine learning, and people, they try to collect more data, put more compute, and make the model a little bit more deeper. And they just start to see, oh, there's a performance increase when they do that, and they are just keep doing this. I think that was the key thing. We kind of develop a method, I would say. When you put more data, when you put more compute, you achieve higher performance. And in other techniques, that we had this problem of overfitting. No matter what,
overfeed them with data and overfeed them. Yeah.
No matter how much you change your model, you may not achieve some performance. But these deep learning models, I think they have these capability. You kind of try to make the model deeper, and you try to put more data, then you see performance improvements. Previously it was more. Now they say it's a little bit slower. But I think that was the key thing for this model development to be adopted in industry.
Okay, so with respect to that, obviously you've addressed a lot of improvements. I mean, you've addressed the computational aspect, the power capacity of the hardware, smarter algorithms, also the component of maybe the sensors, the cameras into the mix. Is there anything then that needs readdressing or addressing to actually ensure that there is full-scale autonomy when it comes to self-driving cars?
Yeah, there's a lot of discussion going on, achieving level 4 is feasible, or level 5 is still hard.
Can you go over those, Oktay? Obviously the levels of automation, just in case people are not familiar with it. I mean, I've always had a question in my own mind as well. We spoke previously about the Airbus automation, what you're striving for in terms of innovation there, and then we've got self-driving cars. I mean, are there any similarities in the approaches taken from a software development perspective and the tools used, and what are the differences? I mean, are we still talking 5-level automation in cars and planes? Maybe you can sort of explain that 5 levels of automation and where cars and planes are.
I can give some information about that. I think there's a definition published by Society of Autonomy Engineers, SAE. So level 0, there's no automation. I think human is supposed to do all driving tasks. For level 1, we have some basic driver assisting capabilities like lane keeping and ACC. And I think level 2 is partial automation. So driver must have hands on the wheel and be ready to take control at any given moment. And automation can give controlling the speed and steering, I would say. Then there's level 3, I think it's called conditional automation. I think most of the task is done by the automation software, but then whenever the software wants to deliver the driving task, the human must be ready and take over.
Okay.
Within a certain amount of time, I think. And level 4, I think in a given location, the car is supposed to drive by itself, and human is not supposed to control the vehicle. And level 5, I think this is the highest. It means it's not going to work only for a specific location. It will work at any location, at any time of day, at any weather condition. I think the level 5 is the highest one. But I think if you have something at level 4, level 3, that's also good for short term. But I can try to explain what we need to solve to achieve these levels, I would say.
Yeah, again, that would be wonderful.
These are my subjective opinion. It may not be true, or I may have limited information on the subject. So when you try to develop an autonomous robotic platform or autonomous vehicle, you have to solve a couple of problems. And the first problem, I would say, the so-called planning and control, maybe, or maybe I should start with the hardest one. So the first problem you have to solve is called perception. So let's say you have a car, you want to drive in a city. Perception is the task of trying to identify the geometry of the environment. And if there are like moving objects, try to understand their types, like is the car or is it truck or is the motorcycle, or try to understand like some other static objects that can be used for driving, like traffic lights, or which light is on, or is there a stop sign. So these are all perception problems. You have lots of sensors on the car. You may have LiDAR, radar, camera, IMU, GPS, ultrasonics, like a bunch of sensors, and they work on different physical principles. So you have all of these raw measurements, and you try to fuse them and try to get a local map around the vehicle. Then you want to place like geometric shapes, like road geometry. Then you want to place all of these moving agents or like other vehicles or pedestrian, whatever. And I think this is the subject of perception. So this is a very difficult problem.
And what I mean, I'm going to interrupt you quickly. I mean, because you sort of started there by saying let's begin with the most difficult one. So why is perception the most difficult one?
Again, it goes
is it
back
the unpredictability
to, like, so when we look at the image, we can understand what is in that image, right? If it's a little blurry, we will have troubles to interpret what is inside, right? But most of the time, when we get a camera image, human, they can identify things very well. But robotic software or autonomy software, they have so much noise in their measurements. When they take a picture, it's not clear. Or when you try to get a measurement from radar, you understand where the vehicle is, but you always have a noise because it is hard to get to reality without noise in it. That's a challenge. The Mother Nature is always against us. She doesn't want us to learn the grand truth. So whatever you measure, it's always there's a noise, and you have to somehow develop algorithms to filter out this noise. And then we get this like sensing capability. Like we see a bunch of, let's say, when we have a LiDAR, we kind of shoot some beams to some certain directions, and it hits and it reflects back. Then we say, oh, there's something there. I don't know what it is, but there's something there. Then from that, you try to understand the shape of that object by just using some like very raw measurements. That's very hard. Like it is very hard for computers to extract patterns. That's very easy for human. Like you don't tell a human what an elephant look like. You just show some pictures of elephant, and then whenever they go somewhere, they can figure out, okay, this is an elephant and not elephant. But for vehicles, like, or for AI software, you have to show maybe hundreds of thousands of same object with different angles so that they can be trained. So that's kind of the key challenge. Like computer software or AI models, they are different than how human brain work. I don't know.
I also think it's somewhat similar in some respect, because obviously if you think about a child and the development of like image to word and word association, and how you teach a child, or even an adult, if an adult approaches a situation and they encounter an elephant, then a lot of the time it's contextualized, it's their own schemata that's been contextualized by previous experience or previous exposure to certain knowledge or experiences, and that's why they interpret it as an elephant. So I think that the component of training a model as well to recognize, or a computer to recognize that that is the elephant. I think there's small similarities, no?
Yeah, I mean, we of course always take inspiration from nature.
Yeah.
That's for sure. But I always give this example, like birds, they fly by flapping their wings, but we have aircrafts with fixed wings and they don't flap. But we share the principles, like we know like there's aerodynamics behind it. And I think that's kind of similar thing. Like we know how people learn, how they make decisions, and we try to mimic them, but with a different interpretation. Like computers, they work on a different principle. What I was trying to say, like for perception tasks, we never get ground truth. We always get measurements, and it's always corrupted with noise. First, you have to filter out this noise from those measurements. And I think the other thing is like you have a bunch of like raw information, and you have to fuse them to build a map, for example. And that's very difficult when you have two sensors when they measure conflicting things. Like a camera may say there is nothing, but the LiDAR may say, oh, there's something. So whenever you have these conflicting information, you have to make a trade-off between what to trust or how to blend them. That's also a very like difficult part. So these are the things that make perception a little bit harder. Especially like if you give me a map and if everything is placed there, I think it's not hard to plan a path and drive a vehicle there. So people, they know these perception tasks is super hard, and they say, what if we map that environment before we drive there? and that's the business of something that they call a high definition maps. So there are companies, they say, where do you want to drive? Well, you say, I want to develop a shuttle service. Okay, they just go there and they just take lots of cameras and sensors. They drive in that environment and they try to make a map before driving tests, like offline. That makes perception problem much tractable to solve, because when you have a map, that means you have prior information. Like you have a kind of a sense of what you should see in that environment.
Yeah, what you should see. Yeah.
Yeah. And then whenever you have some measurements on your vehicle, you can compare and you can make a trade-off between what you expect to see and what you really see. Then you can get a sense of like where you are in that map and what are the objects are doing. So like I said, perception is a little bit difficult. And some companies, they say, we are not going to use maps because it's costly to maintain a map. And construction and sites, they change all the time and it's hard to maintain such thing. Some people, they say, well, we are going to map the entire world and we are going to deploy a vehicle to drive by itself. So these are, like, again, different approaches based on different opinions. So let's say you have a good perception software. So you understand your surroundings, you understand other vehicles. And the next problem I would say, and this is much harder, is called prediction. In the prediction task, you will see a bunch of other vehicles moving with you, and you may want to predict their intention. Are they going to lane change? Are they going to cut in, or are they going to make a full stop? And these are very challenging tasks because humans are very unpredictable when it comes to traffic rules. I know there are like lots of rules and regulation. There are even like penalty. They say don't drive under influence, but people are still driving under influence. Or they say like there's a speed limit here. Don't drive faster than the speed limit. But nonetheless, human, they just do whatever they want.
Exactly, and that must be very different in terms of. And I know that we're not deviating dramatically from traffic rules and systems, but I've noticed myself, you go to one culture and there are certain individuals that don't follow the rules, and making a prediction around how different cultures drive as well. I mean, that must be really quite complex.
I mean, I cannot even drive by myself when I go to different cities. I would say like New York.
Yeah.
It's very difficult to drive there because some people I would say there are types driving, like there's defensive driving, aggressive driving, and it's road rage. Like there are certain so many like different problems there. And again, like I said, when you solve the perception problem, you try to understand what is out there at this moment. what's out there. Then you say, I'm gonna predict what's going to happen in the next 5 to 10 seconds. Then you say, okay, I see these objects and they have motion, they are moving around. Then you say, what are they gonna do for the next 5 to 10 seconds? You try to predict their motion. Are they going to cut into my lane, or are they going to slow down? Or especially when you make a lane change, for example, if you see a car on your destination lane, and if it is driving towards you, you may say, is it going to speed up or is it going to yield? So you have to predict these intentions.
And how are they being predicted at the moment? Is it like a rule-based approach? Is it data collection models? I mean, how are you going about the whole prediction complexity?
Like, if you have so much data, you can try to build a model, like an ML model on top of that. But the problem with ML models, like when they give a prediction, and when you ask another prediction for the next time cycle, they can be completely different than each other. They may not have consideration the history. And most of the, like when it comes to like motion prediction, we know that these vehicles have to obey physical laws, you know. You cannot have at one moment a vehicle is at this time, and next 0.1 second the vehicle is like 20 meters ahead, you know.
Yeah.
So they have to kind of obey some physical law. And I think like they use both ML models and they use both like physical models. And there are some key variables to understand their motion. Maybe you can say, is this a motorcycle, or is this a truck, or is a sedan vehicle? Like based on these like high level discrete variables, once you kind of figure out by ML, for example, then you can say, oh, I know how a truck can move, and then you can kind of predict its motion. But there are also some other clues, like, oh, the car is giving a signal to turn left. So that may be a clue, and you can put that clue in motion prediction as well. But usually, you can make advanced models, but you have to provide some data, and usually we cannot measure that data without uncertainty. Like even when you drive on the highway, when they try to turn left, like turn on the left signal, maybe they just forget to turn off their signal. Like that may not be the real intention. So that's why it's very challenging to understand their real intention. And in that domain, I think they use ML model, they use like physics-based models, and they try. And it's very like difficult to make it robust, because you go to a different city, you see a completely different driving pattern.
Very true.
And that's why like there's no one solution that can fit all. So maybe you say, I'm gonna have a like motion prediction model for this city, for drivers of this city. And when you go to a different city, maybe you can turn that. So that's why this prediction problem is a little bit harder than perception, because you are trying to predict the future, and you are trying to predict the action of other human drivers, and that's very difficult.
Yeah, and I think that maybe that's where a lot of automation itself, it's a controversially discussed topic from many different angles. There's the whole avenues of, moral responsibility, of safety, of predictability, which we've just obviously been talking about. And I think that, you've highlighted a lot of the complex considerations that need to go into building full-scale automation. Do you think that there will be in the near term, or is it more of a longer term investment as to it happening and you being able to 100% say that we're very happy?
Yeah, I can say that, like, so some people, they ask me why I switch from autonomous driving to autonomous flight. And when I say I believe autonomous flight is easier, and they're surprised, because they say, hey, I cannot fly an airplane. How could it be easier driving a car? So that's why I was trying to give the key problems you have to solve to achieve high level autonomy. First, you have to solve the perception, then you have to solve prediction. And the next, okay, now you know your operating environment and you know how the vehicles are going to move for like short time horizon. Then based on your task, like you are driving a car or you are flying something, you have to go from one point to another point. So you have to find a path. That's called path planning. And then you have to track that path by using like vehicle control commands. So when you kind of separate the autonomy problem into these tasks like perception, prediction, planning, and control, I would say autonomous driving is easier when it comes to control tasks. It is easier to drive a car, and I mean, even if you don't know what you do, you can pull over somewhere. It's very relatively simpler compared to flying an airplane, I would say. Otherwise, it wouldn't take lots of hours to train a pilot to fly an airplane. So when it comes to control tasks, autonomous driving is easier. Autonomous flight is a little bit more challenging, but we already have some technologies over there. We have flight control technologies that are so mature. It's a challenging task, but we have a solution for that. Let's say for control tasks.
Excellent.
And then for planning, I would say planning a path and trajectory for a airplane. I think airplane is a little bit harder because you have to consider orientation of the airplane. Like you have to plan in a high dimensional space and you have more constraints. But when it comes to perception, I would say autonomous driving is harder because we don't fly in an airplane in a forest,
Yeah, exactly. I mean,
you always fly in a
simple,
very controlled environment,
yeah.
and like when you take off, when you're in the air, there are no objects, and you have predefined routes. So perception problems are much easier in aviation and compared to autonomous driving. But there's another issue there. We usually require high level of accuracy for aviation for safety reasons, and that's maybe a different challenge.
Yeah,
it's a tractable problem, but the expectations are high. It has to be accurate with high degree of the performance is much higher than autonomous driving. And the last piece, I would say, prediction. I think autonomous driving is very challenging for that task. No matter what you do, when you drive things, when you see things that are driven by human, it's hard to predict what they are going to do.
Yeah, I think it's the emotional complexity of humans, as we touched upon earlier, that makes it so difficult.
And for aviation, I would say when you see a pilot, when you fly, when you see another flying things towards you, they have to declare their position and location and intention by law, and that's why those intentions prediction problem are much structured and much easy to handle. Of course, there will be some cases where you have a non-cooperative objects, you don't know what it is, but then you have some certain of predefined plans, I would say. So when you see these challenges, I think achieving level 4 or level 5 is very hard for autonomous driving unless we change our infrastructure.
Okay, yeah. And do you see that happening?
And I mean, like I said, I'm trying to interpret the problem as an engineering way, like from an engineering perspective. If I cannot solve a problem, I should simplify the problem. And if you change the road infrastructure, because road infrastructures were designed for human drivers, not self-driving cars, and they were there for 100 years. So you have to maybe instead of traffic light, maybe you have to put some other sensor that can tell you who can drive and who cannot, and maybe you don't need to use computer vision to understand traffic light. I know there was some videos where the moon or the sun was misunderstood with traffic lights. Like you were the car was driving towards the sun, and the sun was in like orange color.
Okay.
And it was pegged as like a traffic light or something. So there are some challenges, and maybe the city should, or like whoever decision maker there, they should kind of make infrastructure simpler or more advanced so that self-driving cars can drive. And I think that will make perception problems easier. And for prediction problems, if all of the cars are autonomous one day, and if they communicate and exchange information with each other, I think that will also make prediction problem easier to solve. So that's kind of like, I say, okay, it's not hard to achieve level 4, level 5, but I think within the current form, the problem is super challenging. You have to do some structural change in operating environment. We are lucky in aviation because airports are controlled places. They have similar structure. They have nice like patterns. So, and not everybody can go.
Yes, and I think
that's why. And also, like we have limited number of airports in the world, so it's like we can kind of quantify how many airports we have and study each of these things.
Exactly.
We have more structure in aviation, I would say.
Yeah, definitely. I mean, I think it's as you've mentioned and hit the nail on the head there about the controlled environment and the opportunity to be able to bring in a little bit more structure and regulation around the environment that's been interpreted. So I still have a couple of questions that I just want to squeeze in before we end, Oktay. So sure. Obviously today you've communicated so many different interesting angles here about autonomy, about automation, and you can see that you were very passionate in all of your roles that you've embodied. I mean, I don't believe that I've ever spoken to someone who's been so occupied with automation and autonomous systems in such a vast mapping of ecosystems. I mean, you've been in air, you've been in land, even the solar system, which we've not even had time to touch upon today. And we've spoken a lot about self-driving cars, about the challenges there and what you're striving to achieve in that space, both with the self-driving cars and aviation. So you worked for Elon Musk at Tesla, and I'm sure that a lot of people have this question. What's it like working at Tesla with Elon Musk?
I mean, I was a member of the pilot team, and that was very like high profile, high performing, fast paced team. I still enjoy my time, my experience there, I would say. Elon would attend personally autopilot meetings and like on a bi-weekly schedule, I would say. He would give us some high-level guidance about what to do, and I think Tesla's approach to self-driving cars is a bit different than other companies. Many companies, they want to use some other sensors, but Tesla wants to solve a vision-based solution. And I think the company is doing really great progress to achieve that because they have all the pieces to achieve such thing. I would say they have like bright engineers, a good leadership, and lots of infrastructure, data, and I mean Tesla cars, they can collect data at anywhere in the world, so that's a big thing. And I think he was like a very like he would set a goal that is very challenging, and he would expect the engineers to follow his leadership and to achieve that. And he was good in terms of finding bottlenecks in a big organization and try to fix them on the spot.
Excellent.
And I think when you try to organize or lead a big organization, these are the key things. Because in other places, whenever I want to do something, I had to send an email to my team lead, and then he had to send to his manager, then manager to VP, and VP to director. So there's a long line of people in between. But I think Tesla was a quite flat organization. It was engineers, my manager, and Elon. So it was very like clear. The information flow between management and engineers was very smooth and flow.
And do you think that contributes to the success of the company?
I would say Tesla is more of a startup at scale. Autopilot is one startup, battery team is one startup, or like, and I think they are talent magnet. I would say they attract people who want to work for Tesla, and I think that's the number one condition to achieve something in Silicon Valley. You may have a good idea, you may have lots of money, but you have to build a good team. If you don't have a good team of engineers, then it's hard to deliver something. And Tesla was kind of one of the I think one of the places that are desired to work for. Number one, I think, in recent days. So that's why they had so many good engineers, and they had so many good infrastructure, and also people were very enthusiastic with their work, because they knew they are working on something quite like state of the art.
Yeah, the innovation that drives the vision and passion in teams. Yeah.
And people, they were super young, to be honest. I was one of the older guys in the team.
And you're not that old.
but the thing is, like, the entire autopilot team, maybe it was quite young, and most of the engineers, bright engineers, were people with 1 or 2 years of industry experience, but they are kind of success hungry people. And they would just work and work and work to solve the problem until it is done. Like it wasn't the place where you just work 9 to 5. I mean, and many people, whenever they are given a task, they wouldn't let it go until they are done and solve it. That's very something unique, I would say, when kind of like when you work for big companies. I think like you cannot ask people to work more if you pay them more. I mean, like, they have to focus on that problem. They really want to solve
and want to solve that problem as well.
And I think Tesla is a good place to attract those people who are enthusiastic about solving autonomy, and put them in one place and give them good leadership. And I think good leadership is very important. In other companies, like, there were so many of different opinions, everybody is saying something, and it was hard to reach a consensus. But in Autopilot, the goal, the tasks, milestones were always clear, and you just need to work towards those things without looking what's around, what other companies are doing, I would say.
Well, I'm certainly really excited to see what it holds in the future. And I just want to thank you again so much for being here with us today on the podcast. And I wish you the best of success in your own endeavors, and also at Airbus.
Thank you, Lauren. I really enjoy our conversation, and I think this is a great time to be in. And I highly recommend any people who want to study engineering and who want to go to AI robotics, I highly recommend them study these fields, because in the future we will see more AI and robotics products in our daily lives, and I'm just looking forward to it.
Excellent. So I want to thank everyone for listening today. And if you'd like to find out more about Squirrel and the Insight Engine, then go to the Squirrel Academy on learn.squirrel.com and access our educational material. Thank you.